All right, let's talk a little bit about nuclear chemistry. So here's a comparison chart between nuclear reactions and chemical reactions. In nuclear reactions, elements can be converted from one element to the other. In chemical reactions, that doesn't really take place. No new elements can be produced, only new chemical compounds, which are different arrangements of the same elements. For the nuclear reactions, particles within the nucleus, such as protons and neutrons, are involved in the reactions. But in chemical reactions, usually only the outermost electrons, and we're looking at those electron interactions to form chemical bonds. 3, nuclear reactions tend to absorb or release much more energy, typically 1,000 times or more, where chemical reactions are going to absorb or release much smaller amounts of energy. That becomes very important when we start talking about nuclear power. 4, for nuclear reactions, the rates of reaction are not influenced by external factors like kinetics, like we talked about, like where you had a temperature variance on the rate of the reaction. But things like concentration, pressure, temperature, action of catalysts all can impact the chemical reaction rate, but nuclear reactions are going to plot along at the same rate, and it's dependent upon the nuclear stability. So let's look at the beginning of nuclear science. 1896, Henry Becquerel accidentally discovered radioactivity in uranium salts. In 1898, Marie Curie discovered two new radioactive elements in uranium mine residue, polonium and radium. 1898, Ernest Rutherford discovered that radioactivity had two distinct forms, alpha and beta. Later on, we discovered gamma. And so we have a lot to do with the subatomic particles. And this is a bit of a review from the first semester course. But you have your proton, neutrons, and electrons. And so your electron carries a -1 charge and has a very small mass, where in first semester we may have listed that mass, but we just consider it to be 0. We kind of round it down, but it's 0.0005458. When you do certain types of nuclear calculations, you need the precise mass. Protons are +1, and while we kind of said 1 first semester round off, it's 1.0073. The neutron is neutral, and it's close to 1 again, but 1.0087. We do need those precise masses for a calculation we'll do later in the video. So the nucleus consists of protons and neutrons within a very small volume. We have to keep those positively charged particles away from one another. The protons and neutrons are made out of smaller fundamental particles called quarks, which we won't really investigate in this particular course. Nuclei have a very small diameter. We're talking 10 to the -12 centimeters. But its density is very high, 2 times 10 to the 14th grams per cubic centimeter. There's a force called the strong nuclear force that's very much related to how many protons and neutrons you have that holds it together, but only very short distances, causing these particles to stick together. Now, nucleides denote different nuclei. Those nucleides need not necessarily be radioactive, but they can be, in which case become a radionuclide. Isotopes are nuclei that have the same number of protons, meaning they're the same element, but different numbers of neutrons. Experimentally, we can show that nuclei have preference for even numbers of protons and neutrons, but odds are possible. But your non-radioactive elements have a definite preference for evens. And so if the protons and the neutrons are even, there are 157 known stable nucleides. Even odd, 52. Odd even, only 50. Odd odd, there's actually only 4. For example, deuterium has 1 proton and 1 neutron. or nitrogen 14 has 7 protons and 7 neutrons, but there's only 4 of those. There's also a special stability with certain proton and neutron numbers. This is due to shell effects similar to the sp DNF orbitals for electrons, but these are for nuclear particles. The rules for those particles are different than the rules for the electrons, but again, we'll save that discussion for another course. But these numbers that are unusually stable we call quote unquote magic numbers, and those magic numbers are 2, 8, 20, 28, 50, 82, and 126, where 126 only applies to neutrons because we don't have an element 126. If they eventually develop that element, perhaps there'll be some unusual stability, but there's no way for us to know if that extends to protons at this point. But you'll find that combinations of those tend to produce unusually stable nuclei. Here are some examples. Helium with a mass of 4, 2 protons, 2 neutrons, both magic numbers. We call it doubly magic. Oxygen 16, 8 protons, 8 neutrons, doubly magic, where the neutron number is a subscript on the right, and these calcium 40, 20, and 20. Calcium 48 is 20 and 28 because 28 is also a magic number. Doubly magic again. 10 with a mass of 120, singly magic. The 50 is a magic number, but not the 70. Lead 208, 82 and 126, that's a magic nucleus. You find a lot of elements that are above lead and atomic number. A lot of those decay series end in a lead isotope or one or another. Not exclusively, but it's fairly common. So what about nuclear stability and the binding energy? A lot of times we'll look at something called the mass defect, or delta M, which is the sum of the masses of the protons, neutrons, and electrons as individual particles minus the actual mass of the atom. The difference in the mass, because the mass of the actual atom will be slightly less than the sum of the masses of the particles. That mass defect has an effect on the nuclear binding energy or strong nuclear force. Due to the Einstein relationship, we can calculate that binding energy using E equals mc squared. In our case, the M will be the mass defect. So if we look at that, calculate the mass efficiency and binding energy for potassium 39, where the actual mass is 39.3220 per atom. So I've already converted all that over. So let's get our delta M. And it's going to be all these particles. So now potassium is element 19 off the periodic table. So we can get some info off the periodic table. There's potassium 19. Don't go by this. Go by the more precise mass here. But 19 tells us the number of protons. So it's going to be 19 times the mass of a proton, 1.0073, plus, then we got 39, so 19 minus 39 is 20, so it's 20 times 1.0087 plus, we're going to go with 19 electrons times the 0.00054558. All that with units of AMUs. You say, why include the electrons when we've been ignoring them up to this point? The mass defect tends to be small, so we need the extra precision to make sure we capture the defect. So let's figure out what the sum of the mass of the particles are. So it's going to be 39.32. We're going to do it to the same precision. So we're going to call that 30 AMUs minus 39.3220 AMUs. Now, that's why we needed the precision, because you don't really see the difference all the way out in this thousandths place. But, so we're going to say 39.3230 minus 39.3220, and we get 0.0010 to maintain the sig figs AMUs. Not a whole lot of mass defect per atom. We want to get the binding energy. Now what we can do, and there's a couple different ways to do this, we'll get the binding energy in grams per mole or in kilojoules per mole. So we can use a grams per mole conversion, because on the periodic chart, we can say that this is 39.10, for example, AMUs per atom on average, or 39.10 grams per mole. And so use our stoichiometry. So that could be 0.0010 grams per mole. Those are more or less the same relationship. Now, to get the units on the energy workout, I really need kilojoules per mole, or kilograms per mole. So we're going to divide by 1,000. We'll go ahead and go to scientific notation for this. And so that'll be 1.0 times 10 to the negative 6th kilograms per mole. Now we're ready. E equals mc squared. I'll explain why we need to do that once we get the units going. 1.0 times 10 to the negative 6 kilograms per mole. Then we use the speed of light, 3.0 times 10 to the 8th meters per second, quantity squared. So we're going to punch that in our calculator. And we'll get our E is equal to 9.0 times 10 to the 10th. Now let's look at what our units are. We got kilograms, meters squared, moles, seconds squared. I don't really want to leave it there. I want something like kilojoules or some sort of energy unit. So let's work out the units. Now, a joule of energy is a Newton times a meter, where a Newton's a unit of force. That Newton breaks apart as a kilogram accelerated with an acceleration of a meter per second times a meter. And so the joule would have units of kilograms meters squared per second squared. And so we just got the mole kind of hanging out. So that's the reason I end up going to kilograms at this point. So that would be 9.0 times 10 to the 10th joules per mole. If you want kilojoules, knock 3 places off of it. 9.0 times 10 to the 7th kilojoules per mole. But still a rather large binding energy, which you would expect since potassium with a mass of 39 is considered a stable isotope. When this number starts getting smaller, that's when you want to start thinking, hey, this might be a radioactive element. But since it wasn't specific, either of those could be your answer. And you don't have to work through this unit analysis every single time, but I want to show you that it does work out to be joules.